So what we're doing is we're considering atmospheric air to be a mixture of dry air and water vapor. And in doing this, recall when we were looking at gas mixtures, we talked about Dalton's law. So that's where we will start here. And from our formulation of Dalton's law, that led to the idea of partial pressures. Which enabled us to express the component pressure in terms of the mixture pressure and the mole fraction. So consequently, when looking at atmospheric air, what we can say is that the pressure is going to be the partial pressure due to the air plus the partial pressure due to the water vapor. So PA that is the partial pressure due to dry air, and P subscript V is partial pressure water vapor. And that will turn out to be the vapor pressure that we would obtain off the steam tables for the particular temperature that we are dealing with. So typically what we do is we will treat both the dry air and the water vapor as an ideal gas. So we make that approximation. And the temperatures that we typically deal with when we're dealing with HVAC tend to be in the range of about -10 up to about 50 degrees C. Now there are conditions where you can get temperatures lower than that. However, that is typically what we'll be approximating when we go through a lot of our analysis. So looking at making this approximation of air being an ideal gas as well as the water vapor, if we look at a TV diagram for both of them, so there's a TV diagram for both dry air as well as water vapor, and what we can see for the dry air, no doubt it's an ideal gas that we're dealing with because typically the pressures and temperatures that we're dealing with atmospheric conditions would give us the ideal gas characteristics. For water vapor, it's a little bit more of a stretch. However, given that the pressure of the partial pressure due to, or of the water vapor itself is going to be fairly low, 10 kPa or lower, when you look at the constant pressure line on a TV diagram, you'll see that we are able to make this approximation, and essentially what this will enable us to do is it will enable us to simplify some of the equations that make the analysis quite a bit easier when we go through and do HVAC, heating, ventilation, and air conditioning applications. So we treat both of them as being ideal gases, and that is how we will proceed. So one of the characteristics that we have here is when we're dealing with atmospheric air, if you're at a fixed pressure, so fixed atmospheric pressure, and you lower the temperature through cooling, we get very interesting atmospheric phenomena occurring. Some of them could be dew formation. You can have fog formation, you can have rain and even snow depending upon the temperature. And so that is what happens when you lower the temperature. In a northern climate like Canada, what we have is at this time of year, it's in the fall right now, but things are getting a little colder. And consequently, we quite often wake up to see an interesting characteristic or pattern on our cars. And so what I have here is a picture that was just taken a couple of days ago, and we're starting to get frost formation. And so what's happening is the water vapor in the air is dropping out and landing on the car, and then you get nice crystals forming, like you could see in that video clip. And so that is an example of some of the changes that can occur due to temperature. You can also get similar effects if you are able to lower the pressure of the atmosphere relatively quickly. So let's take a look at that. So if you can lower the pressure of the atmospheric conditions, what you can find is you will sometimes get the situation where the dew point changes such that you actually do start to get condensation occurring under your normal conditions. And an example of a process that can occur there, quite often these don't occur naturally in nature, and they're often induced by human activity. And so what we have here, this is a recent flight on a 767 into Tokyo, Narita Airport. But what you can see is on the wingtip, watch there, you'll start to see white formation coming off in the wingtip vortex. That is because you have a very low pressure coming off the wingtip vortex. And within that low pressure, you encounter conditions whereby you can actually get condensation coming out of the air due to that low pressure. So those are two different examples, one being frost formation on cars when things get cold, and another one is when you lower the pressure, you can actually start to see condensation, similar sort of process. And you'll notice that the condensation appeared and then it went away with the wingtip. That's because the amount of humidity in the atmosphere will change as you're flying along, and consequently sometimes you see it and then it will disappear. You're going into drier air, and then you go into another region where you'll have moister air and you'll see the condensation start up again. So those are two different processes that demonstrate the fact that there is water vapor in air, which we all know. And so what we're now going to do, we're going to continue on looking at developing equations that can enable us to solve problems dealing with both dry atmospheric air and water vapor.